You draw your geometry, apply the load, apply the boundary conditions, run it, you get your results. You get the stresses, you get the strains, you get the displacement, compare it with the material properties, and there you have it. Very straightforward. The only thing is that to be able to strengthen your knowledge or your application of finite elements, you have to go back to theory because you have to know its limitation. You have to know why the results are very high in this case, but you're expecting it to be very low. So why are the results high? So we have to study all these limitations that's going on within FE. So if you're actually looking at the field, if we model it as using finite elements, definitely it's going to just be a cup from a field to a cup. And that's a huge difference. Why? Because of these assumptions. So can we do something about that? Sometimes we cannot do anything about that from a pill to a cup. Reason because of a lot of limitations. So the best thing we can do now is to be able to understand what is behind finite elements. Similarly, when you do finite elements, it's very common for students just to click the button and then you get this pretty picture. It's very common for students. And then when you ask them to describe about this red, blue, greens, and this white means what those color means, they don't know how to explain. So try to imagine yourself. If you're going to present something to your company later on, so you're assigned a project and you're going to do a modeling and then present it to top guys there. And when they ask you to explain, you cannot explain. How would you feel? Okay? So it's really difficult, especially if you work in multinational companies that they have to pay or travel going to Europe or US just to give a presentation and end of the day some simple things you cannot explain. Some people can be very rude in presenting. It happens. Okay? So what we're doing now, well, I'm talking about experience because I have to go then back to when I was a physical engineer, I have to go to UK to do some presentation. Some bosses can be very rude, especially they're up there already. So you have to prepare yourself to explain the limitations, the benefits of your model, and so on and so forth. Big bosses don't want to waste their time. So if they don't want to waste their time, you probably don't want to waste their time. Okay? So what I'm saying is, let's study the principle together so that whatever you can get from FE, you will be able to explain. Or from this software. Remember, in finite element mechanics 3, we have this so-called stroke form or bar. So we're just looking at the bar at the moment. What's really limiting to what our knowledge then was we just determined the displacement. You can recall all your mechanics, finite elements in mechanics 3M. It's all about displacement. So now we're going forward and try to calculate the stress. Because what you can get from ANSYS or Abacus, it's all about stress and displacement. So from this hand calculation finite element, how do we determine the stress aside from the displacement? That's the thing that we're going to do. So aside from your displacement, we're going to look for the stress. Okay? So what are the things that we have to know? Because have a look at this one here. It doesn't really mean anything to me at the moment. That's your notes, chapter 24. It's expected that you should already have known all of the background already, but the fact is that was like 6 months ago or even more. So we're going to review it. So what are the things that you should know? If you are looking at the finite element and calculation method rather than using software. So there are quite things to know because we're more static or we're limited to structural analysis, then we simply have is F equal to A multiplied by U. But definitely this one was derived from your stress equal to this one here. Right? So this one is your constitutive equation, this one is your constitutive equation for finite element. So nothing changes really. Now, there's a difference between 1D and 2D when it comes to stiffness. If you can recall, we've done a lot of skeletal structures last time. So what was the stiffness matrix of a bar? It's quite straightforward. Our stiffness is simply EA over L, and then we have 1 minus 1 minus 1 and 1. So that's very straightforward, and we call this one symbolic representation of your stiffness matrix. We can have this one for a truss, we can have this one for a frame, we can also have this one for a beam. So I'll try to go back a bit. Yes. So we have now this one, the bar or the spring, the bar, the truss, the beam, and the frame. So we can have a symbolic representation of our stiffness matrix. Unfortunately, for 2D elements like this one, we cannot have a symbolic representation. So how do we solve those stiffness matrix? By numerical integration, which we will learn later. Okay, just to give you an idea, so this is just one part of your matrix. Yes? So how do we learn the meaning of each of these parameters? So that's our goal. Try to start from scratch, okay, and try to understand what this means for a 2D element. How do we do that? Let's start with 1D element. So what are the things that you should know? So I've shown you quite a number of things here already. So you have an N. What is an N? So let's start with N. What is an N? Things to know. So N will be your shape function. We have another term. What is the partial derivative of that shape function with respect to x? This is your strain displacement matrix. So we're just defining terms, knowing our vocabulary, expanding our vocabulary in finite element. So this one is the strain displacement matrix. Yes? What else should we know? Of course, we have U. U is the displacement. It's a displacement function. So V is a function of your strain displacement matrix is a function of your shape function, and your shape function is a function of your displacement. So we're just trying to expand our vocabulary, no science here at the moment. The other term that we have to know is your Jacobian. So later on we will have a Jacobian. For 1D element, this one is quite straightforward, and we will be able to study that. What else should we know? Jacobian, it's a value mapping from x to c. We'll show that later. So I've already explained displacement function, shape function, strain displacement matrix, Jacobian. What else? There's another term here that we should know. Okay, how to determine your stiffness matrix. So for a bar, we have that equation, that integral equation. Let me check later how this book writes it, but from what I remember, it's the volume integral of the V, E, V, E, dV. Yes, we're going to perform integration. I know you're excited. Me too. We'll do that later. Not a problem. So these are the things that we have to remember at the moment. Once we have this one, we need to get this one. But before we get this one, we need to determine your shape function. Right? And we can get this one by having this one. So, anything else? So integration is for the skeletal structures. That's what we've seen here. We can have symbolic representation. But for 2D elements, we cannot get a symbolic representation. What's the symbolic representation? So this one is your symbolic representation for stiffness for a bar. You probably have seen the beam already, the cross as well as the frame scheme. So what I'm saying is that we cannot get a similar representation for 2D elements. We can just put numbers there. To be able to get the numbers, you have to perform integration. Not integration, analytical integration, but numerical integration, which is rather straightforward, like I said. So, let's have a look at this one here. I would like to go back and look at this one here. This one is in Mechanics 3. I can post it again in our Moodle if you want to. So I'll just put it there for you to have a look at. First things first, you have to know or you have to understand that we have a strong form. Analytical solution, exact solution. Finite element is a numerical solution or an approximate solution. So your continuum mechanics will provide you the exact solution, while your finite element will provide you an approximate solution. What's the difference? I mean, we have already studied continuum mechanics. So the stresses you can get there, those are exact values. In finite element, we will be approximating the values that we can get from this one here. People can call it elementary mechanics or solid mechanics, doesn't matter. It's analytical solution. What we can get from the analytical solution will be that exact solution. And what we can get from finite element is the approximate solution. So that if we're looking at the displacement here, exact, your displacement here will be approximate. You really want. So let's look at the bar. So for your governing equation for a bar, you have this equation here. EAU double prime equal to 0. This one is a strong form. We will explain later why. Because you have to differentiate this displacement twice, just by definition. This is an exact solution. So the solution you can get for you, the value for you here will be the exact solution. So, the problem here is that in some cases you cannot get an exact solution for the displacement U. So to be able to get a value for that displacement U, you probably have to do an approximation method, and one of them is finite element. So let's have a look at this one here. One method in finite element is the method of weighted residual. So the method of weighted residual, in our case, we will use the Lorentz method. So as you can see here in the slide, what we're going to do here is we are, say for example, what we're going to do is instead of using u here, we're going to use an approximate value. So have a look. Initially we have EA, second derivative of that displacement u with respect to x is equal to 0. This one is the exact. Right? Now, if I'm going to use an approximate value there, EA, second derivative of that approximate value, the value here may not be equal to 0. It can be equal to any number, it can be very close to 0, but the value here is not equal to 0. It's equal to a certain value because this is not the same as that. This is close to that, but this is not the same as that. Yes? So you have a person A here. You change it with a person B, will the result be the same? Definitely not. They can be very similar, but the results are not the same. That's the meaning of this one here. So what does the method of weighted residual mean? You multiply this one here with a residual, that will be the weight, and then integrate, and that will equate to 0. So we multiply this one with a weight, integrate, then this will be equal to 0. So this is this method here. And then that value that you get is an approximate value of this one. Now, here you go. This is what we call the weak form. So take note, why do we call it the weak form? Because we only take the derivative once of this displacement. We're after the displacement. If you go back here, we're after the displacement, and we need to integrate that displacement function twice. But for the approximate displacement function, we only have to differentiate once. So that's the difference between a weak form and a strong form. So this one here is the approximate function, and this one here is the weighting function. Take note, we will need all of this information when we move to the elements, which is chapter 24 of your notes. Yes? So you have your weighting function. So next, we're going to just have u equal to u curly bar equal to u for the next solutions. So that's your strong form, and this is your weak form. Strong form meaning you take the derivative of, that displacement function twice. For this one, you take the derivative of the displacement function once. Strong form, weak form. So u is an approximation, or u curly bar is an approximation of u, but we will now use u for the sake of brevity for the succeeding derivation, and w is the weight function. Interpolation functions. We will be having interpolation functions later on, so to be able to understand the interpolations functions here, which is in your notes, we have to at least try to have an understanding here. Okay, let's look at the bar. Just look at the bar. Let's do this one slowly. So this one here This one is your bar, and you extend it, so there's a displacement U1, U2, displacement here, and a displacement there. So if you want to take the displacement at any point along x, what do? You interpolate. Assuming that is linear, so you can simply interpolate. So what you're going to do is have this u minus u1 divided by u2 divided by, or minus u1. Have a look. U minus u1 divided by u2 minus u1, this one. And that is equal to x minus x1 here divided by x2 minus x1. Interpolation. Yes? So you come up with this one here, and then you simplify. So once you simplify, you will have now this one in terms of u1 and u2. Let's explain that. So you have this one now is u minus u. Let me just remove that one. U minus u1 divided by u2 minus u1. Okay? What do we have here? So that is x minus x1. We're just interpolating x2 minus x1. Yes? The thing is, we want to put everything on one side and just u on the other side, because u is our function. So we want to have an equation where we want to determine this value u. Now, what's going on here? Of course, this is a simple operation now. We have now here u is equal to u1 plus x minus x1, x2 minus x1, and then you have u2 minus u1 there. Yes? Now, what you're going to do now is to arrange it. Okay? We're going to arrange it in such a way that u is equal to a certain value multiplied by u1 plus a certain value multiplied by u2. So that's how you want it to be arranged. So in this case, you have now here u1 plus x minus x1, x2 minus x1 multiplied by u2, and then that plus x minus x1, this is minus u1. So you want to arrange it such that this u1 will be there. Okay? And then put it there, so that is minus that minus x. Okay, so you're getting the drift now. So once you simplify everything, you get now this one here. So once you simplify, you will be able to get this one here. Okay? And what are these values? What are these values? what are those values? So here, let me just write them. U is equal to x2 minus x1, minus x. This one cancels out. Now x2 minus x1, and this will be u1 plus this x minus x1, x2 minus x1, this will be u2. So we have a form wherein u is equal to your shape function multiplied by u1 plus your shape function 2 equal to or multiplied by u2. So this is the thing that we want to achieve. So we have now an expression for n1 and n2 shape function. What does the shape function mean? So before that, let's have this discussion first. This one is your n1. This one is your n2 shape function. So again, if you want to write this one in the matrix form, U is the transverse of your M matrix or shape function matrix multiplied by your displacement vector. So here, these are your shape functions, n1 and n2 shape functions. What are your shape functions? Shape functions will be 1 at the node of interest. It will be 0 for other nodes. It represents your displacement. So let's have a look at n1. So in the meantime, just accept this one. So you have node 1 and node 2. Node 1 and node 2. And then, say for example, this value is 1. So this one is your first shape function. So this one will be n1. Meaning that n1 at node 1 is equal to 1. n1 at node 2 is equal to 0. Or the other one, this one is 1, that value there, the magnitude is there. This one now is n2, shape function. A shape function, shape. Shape here is linear. What's our shape here? It's a line, a linear shape function. So n1 is a linear shape function that is 1 at the node of interest, 0 otherwise. n2 is equal to 1 at node 2, and it will be 0 elsewhere or for other nodes. But of course, they won't be 0 somewhere here, but it just be 0 somewhere here. Right? So n1 at 1 is equal to 1. n1 at the other nodes is equal to 0. Shape function, linear shape function. Node 2 or n2, this is your second shape function. n2 at node 2 is equal to 1. This one will be 0 at node 1. So n1 and n2 are all shape functions or interpolation functions, depends on how you use them. They express the shape of the assumed displacements. So n1 at 1 is equal to 1, n2 at node 1, or n2 at node 1 is equal to 0. n1 at node 2 is equal to 0, n2 at 2 equal to 1. Anywhere n1 that you also need to know is, instead of using 0 to L, we're going to map it in such a way that the left hand M is equal to a C. And then the other one is equal to another C. So let's have a look. And 1 and 2, and 1, no 2. So previously, we can have this one to be L. So x can be 0 here, and x can be L here, assuming that we have now this one to be an x and a y. So what we're going to do is to map such that this one now here function. So this one now here will be 0, and we have now here a C1, C at 1 equal to minus 1, and then C at 2 equal to a positive 1. And then you get the same. I mean, this one is still M1, and this one is still M2. And then this C1 at node 1 is equal to this one here. M1 at C1 is equal to, so M1, just going to write that, is equal to this N1 at C1 equal to 1 and 1. So your N1 at 1 equal to N1, N1, 1, 2. So N1 at C2 is equal to 0. So they're basically the same thing. It's just that we're using now a different terminology. So what we're doing at the moment is just trying to learn some vocabularies that we can use later on. So this one down here, you have look at M2. M2 at node 1 equal to M2 at C1. This one is equal to 0. And then you have down here M2 at node 2 equal to node 2 at C2 equal to 1. So just some terminologies there. So take note, what we're doing at the moment is called mapping. Yeah? So we have now studied shape function. We have started with the weak form, and then we determined your displacement or your interpolation shape function. So what we're going to do next is determine another shape function. Right. So here we are. Have a look. We have now here your, okay, I'll try to write this one in a more simpler way. So we started with this one here. So we started with your shape weak form. So from your weak form, just try to write now equal of that weight with respect to x. So W is your weighting function. You have EA, and then you have the derivative of that displacement. I won't put curly bar anymore. With respect to x, that is now equal to your weight, E derivative of u with respect to x. And then this now is from 1 to 2. So that should be 4. So let's have a look at this one out here. We have understood already our shape function. Let's have a look at this one. So the thing here is that for Galerkin's method, Galerkin's method, the weight function is chosen to be the same as the shape function. So I'm going to write here Galerkin's method your weight function is equal to your shape function. Okay? So that we can have now your weight to be either N1 or we can have this one to be N2. So what about your displacement or strain displacement matrix? What are the values of the strain displacement matrix? So your B, strain displacement matrix, is equal to the derivative of your shape function with respect to x. So we can have your B1 equal to the derivative N1 with respect to x, and then we can have your B2 to be the derivative of N2 with respect to x. Yes? So let's do this one slowly. So if W now is equal to that, then we can simply substitute, yes? So let's have a look at say N1 first. So that weight function equal to N1. Let's have a look at this one. So what do we have? So this is the integral En1 with respect to x, EA, modulus of sectional area, derivative of your displacement function with respect to x. This now is equal to, this one now is equal to N1. And then we have EA, derivative of u with respect to x, from 1 to 2. Let's try to expand further. I'm just writing down this one here, dn1 dx ea du dx. This now n1 ea du dx at node 2 minus n1 ea du dx at node 1. So what can you say about this one? Now let's go back again to the definition of our shape function. So that is n1 and 2. So these values are 1 and 1. Yeah, this one is your node 1 and node 2. So what can we say about n1 at node 1? n1 at node 1 is equal to 1. n1 at node 2 is equal to 0. So have a look at this one here. n1 at node 2, 0. n1 at node 1 is equal to 1. Yeah? So that simplifies things already. So have a look at this one here. So once you expand that, d1, I'm just using dn1 dx at the moment. So du dx e d replace their dx, dx. Okay, because it's still a line integral, so it's dx. So once I multiply a with dx, then that becomes a volume. So it's still a line integral. So have a look at this one here. So I'm now going to move to the next slide, so please remember that. So recall now that n1 at 2 is equal to 0, n1 at 1 equal to 1. So we are now left with this one here. So let me further simplify this one here. Okay, just try to explain a bit. So we have now here that integral en1 dx, ea du dx, dx equal to n1 at 2 is equal to 0. So this now is 0. n1 at 1 is equal to 1. So we have this one to be minus ea du dx. Yes? This one will be, say, 1. Still not 1. Now, since b1 is equal to en1 dx, and we have your volume is equal to dv is equal to a multiplied by dx, we can now simplify this one to be the volume integral of b1 e du dx dv. And this is now equal to minus ea du dx at 1. So we got 1. What do we have next? The next thing that we have to do is look at this one. What is the equation of a force? So recall. Yes. Stress is equal to the force all over the area. We know that. What about your constitutive equation? Stress is equal to modulus multiplied by your strain. What is your strain? So if you have a small displacement and then your length is dx, so your displacement is du. So originally your length is say dx, and then you stretch this one here such that you have this one to be du. What will be your strain? Du dx. So this one now is E du dx. So if E du dx, create both stresses, F all over 8 equal to E du dx. F now equal to EA du dx. EA du dx, we'll just use the positive value 1, so if it's at 1 then it's F1, yes. So EA du dx, F equal to EA du dx, so that is, we'll just ignore the negative value, so this one becomes F1. Yes? So all All in agreement? So we have now here the volume integral. The volume integral of that b1 e du dx dv equal to f1. So we got one. Okay. Now we do a similar thing. So if we let w equal to your second shift function, we're definitely going to get, we'll have a look at that. We're definitely going to get, if we let w equal to n2, we're going to get